Today we will discuss one more theory related to the chemical kinetics, which is called as transition state theory. Okay, this theory is called by different names. It is called as transition state theory, also it called as activated complex theory or theory of absolute reaction rates. Okay, the transition state theory is also called as conventional transition state theory. This theory was proposed, okay, earlier by Henry Eyring in 1935. And though this theory in the later years went certain modification or alteration, but the main idea of the theory is almost the same in the present scenario also. Okay, so this theory is one of the better theories, okay, compared to the earlier theories such as collision theory or um, the Arrhenius theory. Okay, in the earlier theories of reaction kinetics that we discussed, that is collision theory or Arrhenius theory, the collision of the reactant molecule, okay, was considered as one of the important factor that decides the rate of the reaction. However, in this theory, the collision is not considered as the important or the deciding factor, okay, which controls the rate of the reaction. Here, the emphasis is on a species which is rather a hypothetical species called as activated complex. So this theory assumes that, okay, a reactant molecule before forming product, it passes through a state of very high energy called as transition state, and in this transition state a species called as activated complex is formed. Okay, and the structure and the stability of this activated complex is a very important factor that decides the rate of the reaction. So in this particular theory, the emphasis is not on how many times the reactant molecules are colliding with each other. The emphasis is on the formation of a species called as activated complex and its structure. Okay, so that decides the rate of the reaction. So before going into the details, okay, like such as what are the assumptions or postulates of this theory, first let us try to understand the meaning of transition state and activated complex. So what is the meaning of transition state or activated complex? Okay, that we will understand, then we can study the assumptions and postulates of this theory. Okay, so let me consider a chemical reaction A plus BC giving AB plus C. Okay, as you can see, in the reactant side you have A, okay, plus a molecule BC where you have a bond, a chemical bond between B and C, atom B and C, and on the product side you have a molecule AB, that is a bond between A and B and C. Okay, so this chemical reaction consists of breaking of the bond between B and C and making of a bond between A and B. Now let us try to understand this reaction from the point of view of activated complex. Okay, how this activated complex is formed. For that, let us try to imagine ourselves these two reactant molecules initially separated by infinite distance, and what happens to the potential energy when these two molecules come close to each other and form a bond or undergo a chemical reaction. Okay, so before that, let us try to understand what do you mean by potential energy diagram. Okay, say for example, okay, I will keep this reaction aside. Say for example, I am considering formation of some molecule A2. So for the formation of the molecule A2, it is necessary that the two atoms of A should combine with each other. Okay, now let me plot a graph of potential energy versus r, that is the distance between the two atoms, and try to analyze what happens to the potential energy as the distance between the two atoms okay, vary. Initially, let us assume that, okay, so one atom is here, okay. If I take this as origin, okay, here r is equal to 0, that is the origin. So one atom is here, okay, somewhere here, okay, atom A, which is at origin, okay. This moves towards infinity, right of the x-axis. So initially the two atoms are infinitely separated, okay. I will draw a baseline here. The baseline I am drawing here, it is the reference line which corresponds to potential energy 0. What do you mean by this condition, potential energy 0? It means there is no interaction between the two molecules. So all the energy is in the form of kinetic energy, and since there is no interaction between the two molecules, its potential energy is equal to 0. So any point below this reference line, it represents negative of potential energy, meaning that there is a force of attraction between these two atoms. Any point above this reference line which corresponds to positive of potential energy, it means or it corresponds to the repulsion between the two atoms. So when the two atoms are infinitely separated, there is no interaction between them. So at infinite distance, the potential energy will be equal to 0. But when these molecules, two molecules approach each other, okay, but here I assume that one of the molecule is fixed at A, so I am only considering the approach of this atom A, not molecule, atom A. So when this atom A approaches the other atom, so the distance between the two atom decreases, okay, but at large distance there will be no interaction or very less interaction between the two atoms, so the potential energy will almost be equal to 0. But as the distance decreases, the two atoms, okay, feel each other, the approach of each other. The electron cloud of one atom, okay, it exerts some kind of influence on the electron cloud of the other atom. So they start feeling the presence of each other. So there is an interaction between the two atoms, and that interaction is attractive in nature, because the electron cloud of one atom is attracted by the nucleus of the other atom. Similarly, the electron cloud of this atom A is attracted by the nucleus of the other atom. Of course, along with that there will be electron repulsion, but the overall effect is that the attractive force will be more or greater than the repulsive force. So the overall, when the two atoms approach each other, the net effect is there is an increase in the attraction. And I have already told you, when there is an attraction, the potential energy decreases. So when the two atoms come close to each other, the potential energy decreases, and it reaches, okay, it decreases and it reaches a minimum value, okay, minimum value. Now it means the atom is somewhere here. Now the atom is somewhere here, corresponding to this potential energy, where the force of attraction between these two atoms is maximum. Now if I try to bring this atom further close to this particular atom, what happens is, now the repulsive force between the two atoms overcomes the attractive force, because the electron cloud of one repels the electron cloud of the other. Similarly, the nucleus of the one atom repels the nucleus of the other. So this overall repulsive force will be dominating compared to the attractive force. So if I further try to squeeze the distance between the two atoms, it results in greater repulsion, and therefore the potential energy increases. And the way potential energy increases is much faster, okay. For even a small decrease in the distance between the two atoms, there is a sudden increase in potential energy. So this is the potential energy diagram corresponding to the formation of molecule A2. So where in this particular location, where exactly the molecule is formed? At this distance, okay, when the two atoms are separated by almost infinite distance, there is no interaction between the two atoms, so there is no way a molecule is formed. But when the two atoms approach each other, as the distance decreases, there is an increase in the force of attraction, and therefore the potential energy decreases. It becomes more and more negative, and the force of attraction is maximum and the potential energy is minimum here. So this corresponds to a situation where this molecule A2 is formed. So at this particular point, which corresponds to the lowest or the minimum potential energy, this corresponds to the formation of the bond between the two atoms. Okay, so this point here, I will take it as REQ, which is an equilibrium distance between the two atoms. So this length, okay, so this length between the two atoms is nothing but representing the bond length. Okay, so at this equilibrium length, the potential energy is maximum, the molecule is in a highly stable state. Beyond this point, to the right or to the left, okay, it represents a higher potential energy state where the molecule is not stable. So this represents the formation of a bond and therefore the formation of the molecule. So this is how a molecule is formed, okay, by the combination of two atoms which were initially infinitely separated and they were brought close to each other, and at a particular point the molecule is formed, the bond between the two atoms is established. So this is the nature of the potential energy diagram representing the combination of two atoms leading to the formation of a molecule. Okay, so let us take this knowledge to this particular reaction. Now here, if I take the reactant side, okay, so how would the reactant side look? Okay, the potential energy diagram for the reactant side. So this represents the potential energy, this represents the distance. Okay, so I have A plus BC. Okay, A plus BC. So A is a neutral atom, it's an atom. Okay, so I keep it as such. Here I have BC. So let me draw the potential energy diagram for BC. Okay, so the potential energy diagram for BC will be something like this. Okay, the potential energy diagram for BC will be something like this. Okay, so this is RBC, and we'll assume that the potential energy of A is 0 because it is an individual atom. Its potential energy is equal to 0. So this potential energy diagram represents A plus BC, where this condition, this minimum potential energy, it represents, okay, the bond, corresponds to bond length in the BC. Okay, and this particular point represents a point where B and C are infinitely separated. Let me now concentrate on the product side, and let me try to draw the potential energy diagram for the product side. Okay, for in the product side you have a molecule AB and a free atom A. So the potential energy diagram that I am going to draw is mainly for this molecule AB. Okay, assuming that its potential energy is equal to 0. So let me draw the potential energy diagram. Okay, the only difference what I do is, okay, I draw the axis in the opposite direction. Okay, I draw the axis in the opposite direction. So this is the potential energy, y-axis. This is the length, the distance between the two atoms, RAB. Okay, so this is the zero potential energy. How the potential energy diagram will look? Okay, now this represents infinite distance. Okay, so the potential energy diagram will look something like this. Okay, the potential energy diagram will look something like this. So this distance corresponds to the equilibrium length, which is nothing but the bond length AB. Okay, so this represents the bond length of AB. This represents the bond length of BC. Okay, so this overall potential energy diagram is for this particular state. Okay, that is AB plus C. So this is the how the potential energy diagram look for the reactants of this particular chemical reaction, and this is how the potential energy diagram looks for the product side of the chemical reaction. Now what I will do is I will bring these two potential energy diagram close to each other and try to overlap these two potential energy diagrams. So when I overlap these two potential energy diagrams, how the resultant potential energy diagram will look like? Okay, So the resultant potential energy will look like something like this. Okay, just imagine these two being brought close to each other, and when these two are brought close to each other, this side of the diagram will not be affected. Similarly, this side of the diagram will not be affected. Just these two corners of the diagram, okay, they will overlap with one another. Rest of the things will not be disturbed. So if I overlap these two potential energy diagram on each other, the potential energy diagram will look something like this. Okay, so this is the potential energy diagram for the reactant. Okay, it pass to a maximum like this. Here I am overlapping the potential energy diagram for the product. It will be something like this. Okay, here this I will take it as it is some bond. Okay, because I have mixed the x-axis, I have overlapped the x-axis of both the potential energy diagram. So I will take it as reaction coordinate. Here reaction coordinate is some type of bond between two atoms, okay, which keeps on changing during the chemical reaction. So this is the potential energy diagram. This is called as reaction coordinate. What is reaction coordinate? I will exactly tell you later. So if I combine the two potential energy diagram, this will look something like this. So this corresponds to the stable molecule BC, which is ready to combine with A, and this represents the stable molecule, that is the final product, stable molecule AB plus C. Okay, so this end is the potential energy diagram for reactants. This is the potential energy diagram for the product. Okay, what we observe here is, okay, if I eliminate all these extra lines, okay, I will eliminate because these are not significant. Okay, I will keep only that part of the curve which is interesting here. Okay, so what we observe here is the reactant, if it has to form the product in the potential energy diagram, we see that the reactant has to pass through a state of higher energy before forming the product. So without passing through this state, okay, it is not possible to form the final product. Okay, this is not a new concept. Okay, this concept was earlier proposed by Arrhenius in his Arrhenius theory, and it was continued in the collision theory. So this is not a new concept. Okay, this is already known thing, that a reactant molecule, in order to form product, it has to pass through a state, it has to pass through a barrier. Okay, until and unless it does not cross this barrier, it cannot form the product. Okay, and how it can cross this barrier? It can cross this barrier by acquiring excess energy, which is largely because of collision. But what did this collision theory or Arrhenius theory did is, they only concentrated on the collision factor. They did not concentrate on the nature of the species that existed at this point. Okay, so this point of highest energy is called as col, col. Okay, this point or region of the graph or diagram or curve is called as col, col. Okay, so in the earlier theory, that is collision theory or the Arrhenius theory, they did not emphasize or discuss about the nature of the species that exist at this particular point. What in transition state theory did is, they emphasized, okay, and they tried to understand or manipulate the nature of the species that exist at this particular region. Okay, therefore this particular point is very important. The species that exist at this particular point and which has the highest potential energy, the species that exist here is called as activated complex. Okay, so this is a purely hypothetical species. Okay, this species cannot be isolated, it cannot be separated, it can only be imagined. So it is a hypothetical species. Okay, this activated complex is completely different from an intermediate. An intermediate can be easily isolated, and you can detect the formation of intermediate by spectroscopy. But this activated complex is a purely hypothetical or imaginary species, which cannot be isolated, nor it can be detected by any spectroscopic means. Okay, so the species that is formed here is called as activated complex, and the state at which this activated complex is formed, that state is called as transition state. Okay, so the state through which the reactant molecule has to pass to form the product, that state is called as the transition state, and the species that exists at this transition state is called as the activated complex. So what is the structure of this activated complex? Let us try to understand. Remember, the structure of the activated complex is very important in deciding the rate of the chemical reaction. Okay, the activated complex has a structure or structural features of both the initial reactant as well as the final product. Okay, but however, in some reaction the structure of the activated complex will be much closer to the structure of the reactant, and in some reaction the structure of the activated complex will be almost closer to the structure of the product. Okay, generally the structure of the activated complex will have features borrowed from both the reactant as well as the product side. So let us try to understand the structure of the activated complex by taking this simple chemical reaction. So let me take the two reactants. Okay, I have on one side a reactant A and the other side I have reactant BC. Okay, so initially they are infinitely separated. When they are infinitely separated, the potential energy of interaction between the two reacting species, that is A and BC, will be equal to 0. Okay, so initially the molecule A and the molecule BC are infinitely separated, so they do not feel the presence of each other. So there is one full bond or complete bond between B and C, and there is no interaction between A and B or A or C. They are infinitely separated. But once they come close to each other, okay, they start feeling the presence of each other. They start feeling the presence of each other. So when this atom A comes closer to each other, okay, what it will do is it will push the electron cloud between B and C towards C. It means the length of this bond BC starts getting elongated. It means it is getting weakened. Okay, so when these two species approach each other, the interaction between A and B, the electron clouds of A and B increases. So there is some sort of bond formation between A and B, and simultaneously these electron clouds will be pushed towards C. So the bond length BC starts getting elongated, or in other words the bond BC gets weakened. So when these two atoms come closer to each other, a state will be reached, okay, where the bond between A and B is partially formed. Okay, that is why I have shown it by a dashed line. It is not a complete or a full chemical bond, it is a partial bond, okay, formed between A and B. And at the same stage, simultaneously, the bond between B and C is not completely broken, it is about to break. Okay, it is about to break but not broken, and the bond between A and B is about to be formed but not yet formed. Okay, so this is a purely imaginary state called as transition state, and this species is called as activated species or activated complex. So in the activated complex, the concerned bond which has to be formed is not completely formed, and the concerned bond which has to be broken, okay, which has to be broken, is not completely in the broken state. So this is completely formed, this is completely broken. So this type of intermediate state is called as transition state, and the species that exist is called as activated complex. As and so this is the direction, okay, how the two molecules or atoms approach each other. Now with the time, okay, so this atom approaches B further close, okay, and what it will do is, resultingly, this atom C will be moving away from atom B. So after a certain stage, the bond between A and B will be formed, and the bond between B and C will be completely broken, and these two will move in opposite direction. Okay, so this is the initial state, the reactants which are infinitely separated approaching each other, and at a particular state the presence of A, okay, due to the influence of the electron cloud of a partial bond is formed between A and B, and the bond between B and C is completely broken. And when this atom further approaches B, okay, at a particular stage, at a particular distance, there is a formation of a complete bond between A and B, and simultaneously the bond between B and C will be broken. So you get the final product A, B and C, which depart from each other. Okay, so this species is nothing but called as activated complex. It is generally represented by the symbol double dagger. Okay, so whenever I am using this symbol, it means it is the activated complex. Sometimes we use the symbol X double dagger to represent the activated complex. So if I again read out the potential energy diagram for this reaction, so potential energy versus reaction coordinate. What do you mean by reaction coordinate? Reaction coordinate is a parameter that can be used to measure, okay, to what extent the reaction has taken place. Either it can be one of the bond length, or it may be one of the bond angle, or it may be any geometrical parameter associated with one of the molecule, which varies as the reaction proceeds. For example, here I can take reaction coordinate as the bond length, the distance between atoms A and B, or the distance between atom B and C. ಯಾಕಂದ್ರೆ ಈ ಕೆಮಿಕಲ್ ರಿಯಾಕ್ಷನ್ ಇಲ್ಲಿ ಆಗ್ತಿರ್ಬೇಕಾದ್ರೆ, okay, as the reaction proceeds, when the two molecules or atoms approach each other, there is a continuous change in the distance between the atoms A and B, and there is also the continuous change in the distance between the two atoms B and C. The distance between the two atoms A and B, it decreases with the reaction, whereas the distance between the two atoms B and C, it increases with the reaction. So chemical reaction ಆಗ್ತಾ ಉಂಟಂದ್ರೆ there is a continuous change in the distance between atoms A, B and distance between atom B, C. So ಅದು ಎಷ್ಟು ಡಿಸ್ಟೆನ್ಸ್ ವೇರಿ ಆಗಿದೆ ಅಂತ ಮೆಷರ್ ಮಾಡಿದರೆ we can measure the extent to which chemical reaction has taken place. So a reaction coordinate ಅಂತ ಏನಿದೆ, it is one of the parameters which vary during the course of the reaction. That parameter may be one of the bond lengths which vary during the reaction, or it may be a bond angle which varies during the reaction. So let me draw the potential energy diagram again, okay, which is something like this. So this is the reaction, which is A plus BC. This is the final product AB plus C, and the activated complex is given by this structure, okay, where the bond between A and B is not completely formed, the bond between B and C is not completely broken. This is a purely hypothetical structure which cannot be isolated or which cannot be detected. Though it is a hypothetical species, it has a very important role in transition state theory to explain the nature of a chemical reaction and rate of a chemical reaction. Okay, so this is the significance of activated complex or transition state. Now we will try to understand what are the different assumptions or postulates of transition state theory.